that we can use for data science. And within that exploration, we have looked at, we've already looked at two, and we are looking at the third one right now. We've looked at pandas, we've looked at NumPy, now we're looking at Matplotlib. So just to give you a review, Matplotlib is a basic visualization software that we use for data science applications. Visualization is a major part of data science, where we try to look at data, we try to plot data in different graphing environments, and just by plotting the data and visualizing the data, it gives us more insight into what this data is about, how it is distributed, what are the values, can we see a pattern or not, which becomes very difficult to look at raw data and identify. Okay? So visualization helps us a lot, and within that scope, or within that context, we have looked at several different plots in the last class. So let me show you a few again. So here I'm calling matplotlib.pyplot as PLT. So I'm importing matplotlib.pyplot as PLT, and PLT is the standard short form that we use for these plots. We call this, we also write this command %matplotlib inline that helps us to plot that helps us to put the images or the figures that we get from Matplotlib within the Jupyter notebook, within the Jupyter environment. We saw how to create a figure and axis, a difference between figure and axis. So figure is the big set, and within the figure you are creating an axis. So figure controls what is the size of the figure, dimensions of the figure, and so on. Axis gives you more control into x-axis, y-axis, the values that you'll be putting. So there are different hierarchies at which it is working. Okay. We also saw that how to create a line plot, how we can, if we just do plt.plot in the background, we don't need to write figure and axis. Matplotlib manages that. For more control, generally we will create figure and axis. But in most cases, if we just have a simple plot to make, you can directly use plt.plot and get your job done. We saw how we can plot multiple lines in one graph. We saw how to control the color, and we saw several ways of defining the color of the plots. We saw how to control line style. We saw how we can combine both of these guys, that is color and line style, together. We saw basic commands like setting the X limit, Y limit. We also saw we can reverse X limit and Y limit using X lim and Y lim. We are looking at the access command. Okay, let me keep going ahead. We saw how to label the X label, Y label, and title. Okay. We saw legends. That is, once we are drawing multiple plots in one curve. So actually, I'm just revising. This is something that we've already done. I don't want to spend a lot of time on this. Before going ahead, quickly revising what these are. Okay, so we can define labels, and using labels we can do legends so that we get this legend curve. Go ahead. Yeah, then we started looking at, so all of this we saw in line plots. Then we started looking scatter plots. We saw that we can use the line plot, the plt.plot function, not just for line plots, but also for scatter plots. We saw that we can provide a marker like this, plus sign, and this replaces or takes all the data points, and instead of joining them with lines, it draws the different markers. Okay, let's go ahead. We saw the different combinations of markers that we have. So we've got all these characters that we can use. In fact, the list is not exhaustive. We have other characters as well. Let's go ahead. We saw we could combine both scatter plots and line plots, and we can do both things. We also saw we could control each and every aspect. One second. Let's look at uh, this. We can control several aspects of the marker and the line, that like line width. Uh, is, okay, someone has asked a question regarding PyCharm. What is it? What we have to do if I'm using PyCharm to get a plot this graph. Uh, PyCharm is not part of the scope of what we are doing. If we see, if we keep on shifting from topic, we'll never be able to complete anything. So what we're looking at right now is we're looking at Jupyter notebooks, and within Jupyter notebooks uh, we're using the Anaconda environment within Jupyter notebooks to work with our Python commands. And what I'm showing you right now is Matplotlib. Okay, if you want something separate, you can quickly do a Google search. Actually, you don't. Uh, Google will help you a lot with getting plots with PyCharm. Okay. Uh, Someone asks about access command. We have already covered access command in the last class, since I said we were doing a review, but nonetheless, let me also explain what access command is. Okay, just for completion. So the access command basically helps us to control the x limit and y limit. Okay, so we saw here, if I'm using a plt.plot with this command, if I do plt.x limit, I can control what is the x axis starting from, where does it end, what is the y axis starting from, where does it end. Along with this, I could have also used the access command, which basically takes a list of items where the values are xmin, xmax, ymin, and ymax. And thereby you can control what you are plotting on the x-axis, how much you're plotting on the y-axis as well. Okay. Apart from taking just numbers, it can take strings as well. And these strings are some defined quantities within defined var axis, like tight, equal, and so on. That basically says how I want my x-axis and y-axis to be plotted. Okay, I hope this helps. Okay, let me go ahead. Okay, yes, I talked about, yes. Okay, okay. So we saw that within the plot command, we can use scatter plots, uh, and just by providing the marker, we are able to get what the plot looks like. We are able to define certain parameters of the scatter plot. The trouble with that is, if I want to control the individual points, okay, if I want individual data points to be of different colors or of different sizes, then I cannot control it with the plt.plot command. I have to go much deeper. And one such option is using the plt.scatter command. And the plt.scatter command uh, gives me additional control. So here is a simple example where I put x and y and marker as O. So we can see that we have got our sine wave as earlier. We have got at x and y different points. We are plotting with marker O. The interesting thing comes when we are also able to control the color and size of each of the points separately. So this is what we discussed also in last class, how we can control the color, the size, the alpha parameter basically controls the transparency, and so on. Then we said that, okay, let me take some more realistic data so that we can work on it. So we looked at the iris dataset. And for the iris dataset, we saw that there are 150 samples of data with 4 columns. And we have a target variable. The target variable is 0, 1, or 2, depending upon what is the category of flower, that is setosa, versicolor, or virginica. We saw how to get, for the first few points, we saw how to do its transpose. And finally, we took all of this data and gave it to plt.scatter so that we can visualize our data. And we saw that this, even with a simple plot like this, we are able to do a 4-dimensional plot. That is the x coordinate, y coordinate being petal length, sepal width. Then we have color, and then we have size. Okay, so these were the 4 dimensions that we could draw in a simple graph like this. which is very interesting because now the main thing with data sciences uh, or the main need for machine learning algorithms is because we have to deal with something called as multi-dimensional data. And with multi-dimensional data, it will be better if we can view as many dimensions as possible. The more dimensions we can view, the better we can understand regarding our model. And that is one of the problems that humans face, that we are limited by our visualization capabilities. Thereby, we lack pattern recognition up to that point. So, if there's a multi-dimensional data, it becomes very difficult for us to identify patterns. And that is where machine learning algorithms come into place, where they have no such limitation and uh, they can work it out. Okay. So data visualization is our tool, or it's our help in between these space, where even if there is a multi-dimensional data, at least we can see a few dimensions and get an overall view of what the data looks like. And if we are able to do that, then we can, as a data scientist, we'll be able to better identify patterns, better define algorithms, and so on. So we had seen this, and this is where we had stopped in the last class. This class onwards, we will continue with more few plots. I think histogram is the last kind of plot we will see here, and then we'll move to a different package called as Seaborn. Okay. So this is an example of a histogram. Can you anyone type in the chat? What does a histogram show, or what does a histogram measure or represent? Okay, excellent. Histogram measures frequency, which is exactly right. So right now what I'm doing is I'm creating normally distributed data. So from NumPy, I put np.random.randn. So this is normally distributed data. We've got 1,000 such points, and I capture that into the variable data. When I do plt.hist of data, what I get is I get this curve. So what does this mean? This means that I have different bins of information. How many bins do I have here? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So I have 10 bins of information. That means that these 1,000 data points, the histogram has by default divided this into 10 groups. Okay, and for these 10 groups, it has taken. So let's say for this group, if you plot the frequency of items, or you count how many data points come into this group, you plot that here, so you get this height. So basically we see that the data points maximum come into this group with zero, around the zero area, and then as we start moving towards the positive end, and as we start moving towards the negative end, the frequency of items reduces, which is exactly what I would expect from a normal distribution. So rand n, I know, gives me normal distribution of data. This is what I expect. Okay. So within this, I can control a lot of different things. Let me show you what options we can control. So here, when I'm doing plt.hist with the same data, as here, I can control the number of bins. So in the first case, the default was 10 bins. I can say, okay, I'll change it to 30 bins. So I have 1, 2, 3, 4. I've got 30 such different ranges in which we have divided. We put alpha as 0.5. We can control alpha, which is basically the transparency level. That means this is very especially useful when we are trying to plot multiple items or multiple histograms on the same graph, so that we can see what is in front, what is in behind, if there is overlapping or not, what happens behind the overlap. So those things we can know very well if we have set a transparency factor, in which case we are putting alpha. We can say histogram type to be step filled. So there are different types of histogram. If we want to know the options, we can do a simple help. So if I do help of plt.hist and I execute this, then I can see that I have got something called as Hist type, and the default value is bar. Okay, so I can choose these different types of Hist type. So let me show you what options we have. Okay, so we have bar, we've got bar stacked, we've got step filled. So this is an example of step filled. If I convert that into, let's say, bar, let me show you what that looks like. So bar looks like these individual bars. If we do bar stacked, we see this. So it looks similar to bar for me. If I do step, looks this, and if I do step filled, did this stuff. Okay, so we're going for step filled for now. We can control the color by writing the color command. So here I'm telling steel blue. That is what the inner color is. We can define an edge color. So here I've defined the edge color of red. A line width of 5. Let me make that a bit less. If I put a line width of 2, I can get this neat graph. Okay. Let me also change the edge color to, let's say, black. So we can see that you can actually control a lot of different things within the histogram. If I have to plot multiple histograms in one case, let me show you here. So I'm plotting here 3 histograms, x1, x2, and x3. The x1 histogram, this is the inputs that I'm providing, np.random.normal, 0, 1, and 100. So I don't know if you remember when we were doing NumPy random generation, we looked at the normal command. Can you tell me what 0, 1, and 1000 stands for? What do I want as 0? What do I want as 1? What do I want as 1000? Can you describe that? Okay, 0 to 1 with 1000 numbers between. Okay, any other ideas? Okay, you can also get a hint by looking at these values of x1, x2, x3 and looking at this plot x1, x2, x3 that we have plotted. Okay, 0, 1, 1000 has given us this blue plot. -2, 1, 1000 has given this orange plot, and 3, 2000 has given this green plot. Okay, it's okay. Let me tell you what the answer is. Okay, so if you look at 0, 1, 1000, this basically says the first input is the mean of the distribution. The second input is the standard deviation, STD, the standard deviation of the distribution. The 1000 is how many points do I want for this mean and this standard deviation. Okay, so x1 basically says mean of 0, 1 standard deviation, and 1000 points. x2 says mean of -2, 1 standard deviation, 1000 points, and x3 says mean at 3, 2 standard deviations, and 1000 points. Okay, so for each of these, so I want 3 plots. For each of these, I want similar, similar configuration. For that, I'm writing a command called as keywords. I'm setting a variable actually, and this variable is a dictionary variable, which has these values. That is Hist type to be step filled, alpha to be 0.5, density to be true, and bins to be 50. Okay, so these are the common keyword arguments that I want. And to the plt.hist function with x1, x2, and x3, I'm providing this keywords item. Okay, and I'm providing this as 2 stars. So if you remember our class on functions, when I provide it with 1 star, I'm actually providing variable arguments of only numbers, variable arguments as form of tuples. Okay, whereas now I'm providing variable arguments in forms of keywords, that is a key and a value. So yes, a dictionary. Okay, so when I'm providing this, all these options are applied to all of these plots, which makes my job very easy because I don't have to write this again and again for each plot, especially when I have the same values. I don't want to change any values. Okay. Further, we are also defining label. The purpose of the label is once we do plt.legend, we will get this labeled legend here. Okay, so if saying x1, x2, and x3, when I execute this, we can see this data. Let's look at x1. So we expect that x1 should have a mean of 0. So if you look at here, x1 is a normally distributed curve which has a mean at 0. That is the maximum number of values we have at center 0. We see a standard deviation of 1. So we see 1 unit standard deviation, which is roughly going from -3 to +3. That is what it, -3.7, something like that, to +3.7. So most of our data or all of our data will be distributed within this gap. We see the second curve, x2, which is having a mean of -2. So you can see that the max of x2 is, or the peak of the most number of items within x2 is at -2. And we've got, again, the same standard deviation as x1, 1000 points. And x3 we see has a mean at 3. So if you look at this peak value, it is somewhere here between 3. And we also see that its standard deviation is 2. So it will have twice the distribution as this. Since it has twice the distribution and we have the same 1000 number of points, we can see that the height is roughly half. So just make it 2000. I expect that we should have the same heights for all three. Do I? Oh, I don't. What about if I increase the number of points? Okay, so the more it is spread out, we actually require a lot more information for us to get the same frequency. Okay, I think now I've gone overboard. I may have crashed my system. Let me see. Okay, I need to study more about this also. Anyways, so we have seen we can have a histogram which helps us to see the distribution of our data points, and this distribution of our data points can give us a lot of information on what is the min value, what is the max value, where is most of our data, is our data skewed or not, and questions like this. Okay, so this was our basic regarding Matplotlib. Of course, there are many more things within Matplotlib, and our discussion will never end if we start discussing all the different plots we have. But what we have discussed so far is enough to get us started. We have seen line plots, scatter plots, we have seen histograms. Okay. Let me now explore or expose you to a different kind of visualization software called as Seaborn. And Seaborn is a bit advanced in terms of what we can get, what we can do with Seaborn. But Seaborn is also built upon Matplotlib. So Seaborn uses Matplotlib as its base and develops wrapper functions that can give us more advanced plots with very, very simple commands. Seaborn also has a very good integration within pandas. So from your data frame directly, you can generate lots of different plots. Okay. Let us look at some basics and how we can get things done. So here I'm, for a comparison, I'm loading Matplotlib and I'm showing you a simple line plot with Matplotlib. And in the second case, I'm also loading, along with Matplotlib as earlier, I'm loading Seaborn. So it's called import Seaborn as SNS. SNS is the alias or the short that we generally use. You're free to use something else, but I would highly suggest use SNS as much as possible. Now, we are using the same plot command from Matplotlib, but we have run an SNS command in between. What we have run is, we have run sns.set that defines the default values for plots of Matplotlib. So you can see what this has done. First, it has removed the default value for sns.set, has removed the black border that we had. It has changed the font of their labels on X and Y. So the text that we have here, we have changed the font to something that is more natural. We now also have a grid, and so that the grid is visible, and not distracting, we have added a background color, a grayish, a pale background color, over which we have grids in white. So it makes it possible to read this data much better. Okay. So even by using just the template of SNS, not even calling the SNS command for plot, we see that we have additionally improved the quality of our plot to something that is more superior. Okay. And generally, the defaults of SNS are much better for most cases. So that we will not have to do a lot of work within our plot. Let us see what other things SNS can do. So we first create some normally distribute some data so that we can use our plots. So within this, I'm using a function called as np.random.multivariate normal. Okay. So what this helps me to do, this helps me to create a normally distributed data, but the normally distributed data is created between two variables. Okay. In this case, actually you can have many more variables, but in my case I've used only two variables, which individually are normally distributed, but along with normally distributed, they have some covariance matrix associated with them. Okay. So here, the two values that the data that I'm providing here to multivariate normal, the first input is the means of the two data. So I want two plots, two distributions, both should have a mean of 0. Okay. Additionally, I'm giving this another input, which is the covariance matrix that gives us an idea of how these two data distributions are supposed to have a relation between them. So we'll not go deeper into this. We are not going deeper into this. The main idea is that we will just uh, generate some data so that we can do visualization. Okay. In normal scenarios, you will not have to generate data like this. Normal scenarios, you can use the data that comes from a data set for different examples. In this case, I just wanted to create something more that I could control and access. Okay. So we're creating these 2000 points, and I load that into a data frame. So I create from this NumPy data, I create a data frame just by calling pd.dataframe. There will be two columns X and Y. And when I do data.head, I can see that these are the values that I have. Okay. So data.shape shows me that there are 2000 values with two columns. And these two columns, these 2000 values are having 0 means individually. And they have some covariance, some correlation between these two guys. Okay. If I want to see some more information, I can do a data.describe, and the data.describe helps me to find out what is the mean value. So we can see for both cases, the mean value is roughly 0. We can see standard deviation. So for X, the standard deviation is 2.2. For Y, the standard deviation is 1.43. You have a min value. You can see all the different quartiles and so on. Okay. So with that distribution, if I have to analyze these two plots, and if the only access I have is for Matplotlib commands, then I can look at the distribution between them by looking at the histogram that we just saw. Okay. So here I'm simply running a loop for call in XY. So here basically call will take two values. So let me put call. If I execute this, you can say that the variable call first takes X, then it takes Y, because it's basically a string, and it breaks the string down into its individual characters. And then we are calling the histogram command with plt.hist on data call. So data X will give me this first column. Data Y will give me the second column. And for both these, we are running the plt.histogram command. Okay. You're also defining alpha to be 0.5, thereby saying that they will have some level of transparency. So we can see both these plots and it will not be a trouble. And we provide the legend, and we say, okay, we provide the label so that we can do the legend. So this is what distribution we get. Now, this is fine, but if I want to have more access, if I want to see more about this distribution, I can go and do something like a KDE plot. Okay. What KDE stands for is KDE stands for kernel density estimation. So here, a histogram gives us the plot in terms of bins. What a KDE plot does is it takes those bins and it smooths it out so that we can get a smooth variation. We can see how the data is going. Okay. So this is an estimation, of course. This is not a true value. This is an estimation of how the data would have been distributed if we were trying to smooth out these curves. And sometimes these are very useful. Now we can also, within Seaborn, so here Seaborn we used Kde Plot, provided the data, and we saying shade is equal to true. Okay. Along with Kde Plot, we could do something called as a distribution plot, dist plot. Okay. And a dist plot is basically the combination of a histogram and a Kde plot. So it gives us the different bins that helps us see how the data is distributed. Along with that, okay, along with that, it gives us the Kde plot as well. That is, it smooths out these values and shows us how the data is given out. Okay, which is very interesting. So here, in both cases, Kde plot and dist plot, we're just providing one input at a time. So when you give one input at a time, it just it does not try to see the pattern between the multiple distributions, but it just gives us one distribution and just that value. So on the x-axis we have values, on the y-axis we have frequency. An interesting thing is we can have a two-dimensional Kde plot. Okay, so a two-dimensional Kde plot. Here we say that on the x-axis, on the first input is what I want on the x-axis. So I give data x on the x-axis, which is here. I give data y on the y-axis, which is here. And now we can see a combined distribution between these two plots. So we can see how x is distributed, we can see how y is distributed, and we can see the correlation between x and y. Okay. Do you know what these kind of plots are called? Or have you seen this kind of a plot before? Okay. Oh, you have not seen this kind of. Let me probably remind you so that you may get some idea. These kind of plots are generally used to describe on a map what are the heights and valleys. Okay, if I'm looking at the map of, let's say, Nepal or something, I could see that there will be a lot of peaks. The peaks are represented as growing concentric circles. Okay, and this color here, either blue or maybe red, would represent growing in height. So there is a third dimension. I have x axis here, I've got y axis here. There's a third dimension, the height, and I'm showing the height by based on colors. I don't know if you must have seen some war movies, and you would see that generals would open up a map with these circles, and these circles represents the hills and valleys within that region. Okay, this kind of a plot is called as a contour plot. Okay, let me write it down. It's called a contour plot. Okay, and what this contour plot shows is this one line. If I just examine this first line, the black outermost line, all of these values are at the same height. Okay, so we can, if you imagine a mountain, and let's say I take a cross section of the mountain, I cut that mountain in between, then the outermost edge will represent the boundary of that mountain. Okay, that is what this outermost line. So all these values in the lastmost represent the same height. When I go to one circle inside, all these values in the second plot represents again one height, and then so on. So as you see, my heights are getting or the boundary of these heights are getting smaller and smaller. That basically says that this, you can imagine this to be a mountain which has its peak here, and on the x-axis it is distributed between this -5 to +5, and on the y-axis it is distributed from, let's say, -3 to around +3. Okay, and we can also see the correlation. That means as x is increasing, the value of y is also increasing. Okay, as x is increasing from -5 to +5, value of y increases from -3 to +3. So now I can see a lot more about my two distributions. Okay, here it just gave me an idea of how the distribution is spread, but here, along with the spread, it also tells me the relation between the two distributions. Okay, I hope this is clear. Let me go ahead. Now we are seeing the next kind of plot with the same data as before. We are seeing a next kind of plot, which is called as a joint plot. Okay, and what a joint plot does is it gives me this Kde plot between x and y, Additionally, it also gives me the Kde plot individually. Okay, so here I'm using this is called as a it's called as a wrapper, I think, or an environment. I forgot what the exact term is. Let me just do a quick Google search. Oh, my net is a bit slow today. Are you able to hear my voice well? Okay. So just Google is slow. I'm not sure, but nonetheless, let's skip what this is called. Basically, what it does is the width environment says that within this block, within the context, within the scope of this block, we'll be using this access style. Okay, we're using SNS.access style as white. So that is what. So let us see quickly what are the different options that we have. If I do help SNS.access style, I can see that for our style, we've got, okay, set style, set Matplotlib parameter style for seaborn theme, plotting context, color palette. Okay, so we will not get it here. We'll have to go to Google and we have to find. We've got some options. One is white grid. Let us see what white grid does. If I copy this, and instead of white, if I do white grid and I execute, so I can see that, oh, on the KDE part, there are these grids. Okay, which helps me to identify what this data is spread out. So revising again, a joint plot we provide. Okay, so this is a different way of providing data. Okay, so in the first case, we provided the series item to this. Okay, we are providing the first input as this option, data X, which basically says that data is the data frame and X is the name of the column. And this is the selection of that series, okay, of this first column. There's a series. We are providing that series as input to Kde plot. Okay, let's look at joint plot, and you may see a difference here. The way that we are providing data here is different. Okay, what is the difference? The first input we are providing is the name of the column. It is not the series object. The second input is also the name of a column. And the third input is the pandas data frame itself, which basically tells us that Seaborn is very well integrated within pandas. Okay, I have to provide the data frame and I have to provide the column names of X and Y. And we are able to, when we provide this, it is able to understand and it is able to plot this plot. Along with joint plot, we are just saying what is the kind of plot we want. So we say the kind of plot we want is KDE. So that is what we get here, kernel density estimation. In the center, we've got correlation. We have colored here. So this color shows us so how the data is distributed. So you can now imagine better, probably even better than this contour plot. We've got a filled contour plot that gives us an idea of how the height is increasing till this point. So we now know that most of our data is associated within 0. It is also confirmed by this height. Okay, if I just observe the X distribution, I can see that most of my data is here. If I observe the Y distribution, I can see most of my data is here, because of which we have a really dark spot in the center. Okay, so that is how a joint plot helps us to identify or to see the distribution of data. Let's go ahead. If we give the kind of plot as hex, we get this kind of figure, okay, which is also very interesting, because now see what happens here is, here we have an estimation of the data, right? A kernel density estimation is the estimation of the data. It is not true divisions. But now with an hex plot, we've got two divisions. We can see individual data points. So let's say this data point, we know this comes from this bar here and it comes from this bar here. Okay. If I do wide grid, probably we will see some grid that will help us. Okay, so we can look at these bars, and the different points here represent the different bars that we're plotting. Here we see a histogram. Here we see a histogram with bins, And here, in this case, we see histograms. Sorry, here we see hex divisions, which represent the individual combinations of each of these bars. Okay, which is very interesting because now we can see the different colors. Darker colors means more data is associated, more frequency there. Lighter colors means less frequency there. Okay. So here, this light color represents one of these bars and one of these bars. Hence, here though we have lot of frequency, since here we have less frequency, our bar becomes, this color becomes very light. Whereas when we are in somewhere in the center, we've got more frequency on both x-axis and y-axis, thereby this becomes a dark color. Okay, I hope joint plots are clear. Let me go ahead. We look at something called as pair plots. Okay, here again I'm loading the iris dataset. So last time we had loaded the dataset for Matplotlib, we had loaded the same dataset iris, but we had gotten that from sklearn.datasets. Now we are taking it from Seaborn. So Seaborn also is a visualization software. So any visualization software, to test different items, we need some datasets. So they have loaded a common dataset, the iris dataset, which has 4 columns: sepal length, sepal width, petal length, petal width, and one target variable, which is the species. In our case, that is Setosa, versicolor, and virginica. So we take that data, and now we want to plot it. Okay. So what we are doing is we are doing first we are doing group by to see where the means of these plots are for sepal length. In fact, okay, this is something extra that I had done just to get some idea. So let me remove it now. We are exploring the SNS.pairplot. Okay, and to this SNS.pairplot, what inputs are we passing? The first input we are passing is the data frame. Okay, so iris is the data frame. Here we are providing that as input. We are providing hue. So hue basically means color. We're saying color should come from the species column. So here the target variable species should define the color, which is categorical. So we'll have fixed colors. So we provide species as hue, and we say height as 2.5, which basically says how our plot should look like. Once we give this as input, this is the output that we get out of it. Okay, let me zoom it a bit out so that we can, or if I can reduce the height. Okay, give it a few seconds to load. Okay, so we get this plot. Okay, and we see what it has done is pair plot or SNS has automatically understood that we have 4 columns: sepal length, sepal width, petal length, petal width, and we gave color as species. So for this species color, we have got 3 colors: Setosa as blue, versicolor as orange, virginica as green. And here, in each case, it is plotting the pairs between one feature and the other feature. So let us look at, there are 2 kinds of plots here. One is this Kde plot, and the other is the scatter plot. Okay, the Kde plot, you get a Kde plot only at the diagonals. Why? Because here in the first case, we are plotting sepal length on the row and sepal length on the column. So this is the Kde plot for the feature sepal length. This is the Kde plot for the feature sepal width. So sepal width on the row and sepal width on the column. Here we have petal length on the row, petal length on the column, and here we have petal width on the row and petal width on the column. So these 4 plots are kernel density estimation plots. So here you can see, especially in this plot, petal length, that the petal length of Setosa is much smaller compared to the petal length of versicolor and virginica. Okay, that's what this plots helps us to identify. Then when we compare, or when we plot, or when we pair one feature with another feature, so let's say here we are saying sepal length with sepal width, we can see that the individual data points are plotted using scatter plots. Okay, so you can see how visualization works out. If you remember, with our Matplotlib, we had done similar, where we had used 2 features on the x and y axis and 1 feature for the color. Okay? And we were also controlling size. In this case, we are not controlling size. in this case, we are not controlling size. Rather, we are just putting X and Y and the target variable. So we see we get combinations of all plots. In fact, the plot here is sepal length and sepal width. The plot here is sepal width and sepal length, which is basically an inverse of this plot. So if you take this plot and you flip it, flip the x-axis and flip the y-axis, we'll end up with this plot. Okay, so these two plots are similar. This plot and this plot is similar. This plot. So the corresponding or the transpose of these plots are always same. Okay. So there's just one command that helps us to plot all of these plots in one go. So you can quickly identify or you can quickly verify the patterns within our hidden data. Okay. So that's pair plots. Along with pair plots, now we're going for the next set of plots, which is faceted histograms. So let me first show you how we are, what data set we are looking. So we are calling another data set called as a tips data set. And this tips data set, if we look at the head of this data set, we see that there are multiple columns. We've got total bill, tip, sex, smoker, day, time, and size. Okay, so this is coming from a restaurant. And from the restaurant, we see that what was the bill. So on a particular table, the total bill was around $16.99, of which tip was, they gave a tip of $1.01. Okay, they gave a tip, the waitress was female. These people were not smokers. This happened on a Sunday at dinner time, and there were two people on the table. Okay, so this is what this data is representing. So this basically helps us to find what is the pattern between these different features and what is the tip they have provided to the waiter, okay, waiter or waitress. So this data, very simple data. We're using this as an example to see our plots. So the plot that we are looking at first is the facet grid plot. And for this facet grid, we are doing a histogram. Okay, we're looking at histogram for multiple features. So let me explain to you what we are doing here. Okay, so here we have first created an additional column called as tip percentage. Why? Because tip percentage will help us give, instead of absolute values, a percentage of tips will help us to identify more about our tipping behavior. So to calculate this tip percentage, we're simply taking the tip, multiplying it by 100 and dividing it by the total bill. Okay, so how much percentage of the total bill is the tip? That is what we have as tip percentage. Now, if you look at the first command, we are calling sns.facetGrid. Okay, so this will create a grid of data for us. And how will this grid be generated? So first we provide the data frame. We're saying that we'll be using the tips data frame for information. We'll have rows as sex, columns as time. Okay, so now we know that sex is a categorical feature which having two values, male and female. So how many rows we'll have? Thus we'll have two rows. Okay, row 1, row 2, one for sex as male, one for sex as female. Okay, so now this was automatically decided by our facet grid. Okay, if we had multiple categories here, we'll have as many rows. Then we have column. So how do we want to define column? By based on time. What are the different options for time? So we have lunch and dinner. Thereby we see that we have two columns here. Okay, one column for lunch, one column for dinner, which makes our grid of size 4. Okay, 2 cross 2, 2 rows and 2 columns. Right. When we put margin titles as true, we can see that next to, okay, so here on the columns we see the title on the top, and for the rows we see the title on the sideways. If we keep margin title as false and execute, we can see that each plot has an individual table which tells about what this plot is showing. Okay, so this says that sex female, time lunch. So I prefer margin titles as true. It helps me look at the data more clearly. Okay. So, but that's a preference. You can choose something else if you want. Now, once we have, so till now we have not told it what to plot. We have just told it how the grid should look like. We have told the number of rows, we have number of columns. Now we'll go ahead and we'll tell what we want to plot. So we're doing grid.map. Okay. So for this grid, we want to map what? We want to map plt.hist. So for each grid. So let's say you come to this grid. So this grid is basically data for time as lunch and sex as male. So for all the people, for all the distribution where we were looking at lunchtime where the waitress was male, this is the histogram. Okay, we're doing PhD histogram. So it automatically understands the context and it says this is the histogram that we're looking for. Okay, so for this distribution, histogram of what? We're looking at histogram of tip percentage. Okay, we also define how many bins we want. So here we are saying go from 0 to 40 in gaps of 15. So now we can look at this plot and we can get much more information on what is the tipping behavior. Okay, so I'll ask you a few questions on this plot just to see if you are able to understand. Can you tell me on an average, are male waiters getting more tips, or female, are waiters getting more tips or waitresses getting more tips? Can you answer that? Okay, excellent. So male waiters are getting more. Okay. Can you also tell me, are we getting more tips during lunch or during dinner? Dinner. Excellent. So you are able to read these plots, right? So we can see by writing a simple command like this, we don't have to go ahead and make 4 plots. I can use SNS Seaborn's Facet grid method so that we can get multiple plots at one time. So at one go, you can do a lot of analysis with our data. Okay. Of course, there are many more things. Let me move ahead. I'm looking at factor plots. So here again, this kind of a plot is called as a box plot, but this is an advanced box plot because we are using multiple things within this plot to show things. Okay, so first we are choosing a style. The axis style is SNS.axis style stylistics. So within this context, whatever we plot will come within this style. Okay, the style is not valid after this point. Now here we are using something called as a cat plot. Okay, SNS.cat plot, to which you see what are the parameters you're providing. The first 3 things that we are providing is basically string items. Okay, what string items? So these are the column names of the tips data set. We are saying data is equal to tips. That means the data frame that we are providing to this cat plot is the tips data frame. And to this tips data frame, we are saying that I'm looking at 3 different features that I'm interested in. I'm interested in the day, I'm interested in the total bill, I'm interested in the gender, that is sex of the waiter or waitress. Okay. Further, we are saying what is the kind of plot we want. I said, okay, we want the box plot. Okay. So with this information, we said this sets up the place. Okay. Now here you look at set axis label. On the x-axis, I'm putting day. On the y-axis, I'm putting total bill. So what is this plot? This plot is a box plot. A box plot helps me see distribution. So you see on the y-axis, we've got total bill. So each plot tells me for this bill, what was the minimum value, what was the maximum value, what is the 25% quartile, 50% quartile, 75% quartile, and so on. It gives me the distribution. On the lower end, what is the difference? On the upper end, what is the difference? And the median value. Okay. These diamonds here tells me that there are outliers within the data. Okay. So this one plot is for, since this is blue in color, you can see this is for males on Thursday. So on Thursday, males got a total bill. So along for males as attending as waiters, the total bill was distributed within this scope. Okay. For females, the total bills were distributed in this scope. So this we have for Thursday, this for Friday, this for Saturday, and for Sunday. So you can see with this plot, we are able to do a lot of various things. Okay. And we did not have to write a lot of code to get this plot. You can get data as tips, that gives you the data frame. The things that we want to see day, total bill, and gender. So x-axis, y-axis, and our legend. Finally, we are able to plot this as a box plot. Okay, so it's a very interesting plot. Let me go ahead and finish it up with the last plot, and then we'll end this class. So here again, I'm doing a joint plot in hex with total bill and tip percentage. So we can see how the total bill is distributed between maybe around $10 to $50. We can see how the tip percentage is distributed somewhere between uh, 5% to around even 70%. So this is clearly an outlier, right? Why? When for a bill of around 9 or 10, for a bill of around $9, someone has paid 70% of that as tip percentage. 70% of 9 is what? So around maybe around 66 for a $9 bill, around $6 or $7 someone has paid as tip percentage. Someone has paid as tip. Okay, but we see that most of our data is around this. So on an average, people are tipping between 10 to 20% or 25% even. So that is the standard tipping for this data set. Whether male or female, we don't know. We have not plotted that information. And this is what our joint plot is showing. Going ahead, we can also do this one interesting plot. And you see, along with our joint plot, along with the normal things, we also have the kind as red. Okay, so you see this one line. This line shows us the regression, or it gives us an idea of how one feature is varying as the other feature is also varying. Okay, so on the x-axis we've got total bill, y-axis we've got tip, and we can see that as the bill increases, the tip also increases accordingly. Thus, percentage is a very good measure for seeing the tip percentage. So I hope this helped. Seaborn and Matplotlib has many more plots, many more commands that we can use. But this is enough for starting us or getting us started, so we can explore with our data sets. Okay. In the next class, we will look at data pre-processing. So we are now moving from looking at packages. We have seen our major packages. There is one more major package that we'll be using, scikit-learn. But I will explore scikit-learn only after we have done some idea of machine learning, which we will soon reach there. The next class onwards, we'll start looking at how do we pre-process our data before passing it to machine learning algorithms. Okay, so pre-processing is again a major part of data analysis. We spend around 80 to 90% of our time within that. So can we display 3D graphs? Yes, we can display 3D graphs. I don't know if this works out. Let me just try again. Okay, somehow my net is not working. Yes, but we can have 3D graphs within Matplotlib as well. Okay. Thank you so much for joining. We'll stop for today. We'll continue tomorrow. Okay, I'll stop sharing. Okay, ma'am, I'll log out now. Okay.